Hi everyone. Yeah. So in this video, I'm going to talk about what exactly I'm working in towards my second Gsoc. So I'm going to discuss my progress so far. And the reason why I'm discussing this is because it's the first time I've actually been involved in an ML project for like now 7 months now. So I was working on this project even before Gsoc started. I understand the infinite screen, but well, yeah, That's all right. So let's get into it, and I'll tell you more about it as time progresses. Right. So small models, big egos. So essentially, what I'm working towards for like 7 months now is using a specialized form of a visual transformer. So, if you're all aware, visual transformers usually process information in terms of patches, right? You have your image as its input, and then you cut it into patches, and then the attention happens in between them, right? But in this case, we are gonna have channel wise attention. So, if I make you understand in a simpler way, suppose this is an image and I cut it into patches, right? This is the normal way of attention where attention tracks between these attention these patches, like cross patch attention for something which is entirely global, right? But if you think about it, RGB values all have a set range of values and all mean the same thing, just a different color, right? But in detector physics, if you have a detector which has different kind of instruments what is working towards, the scale in which they both work may differ a lot. Each detector and its value mean a different thing along its own axis, right? If I give you an example, a thermometer and its reading has a different meaning compared to a barometer and its reading, and the range in between those readings happens also are at a different range, right? So we have developed a new architecture called as a DepthViT, and I've been working on it for the past 7 months. I know I've said multiple times, but the thing is, I got involved in this project in January, along with my Gsoc mentors unofficially, and then I worked for it, and then eventually I got the right kind of project also this year with Gsoc. So it's like a mixture of unofficial and official work mixed. So entirely it's that time period. So let's get into it in terms of what exactly I've been working on, so that I would say it's like a good introduction to something which is quite prevalent nowadays. That are small language models, or like small vision models in this case, which help a lot in terms of deployment, right? So this is the TLDR results. Of course, we'll get to know about it more as time progresses in this video, right? So why we have to use compact models? So in a Large Hadron Collider, in a particle accelerator, every 25 nanoseconds there are like number of collisions that happen, okay? Some of those collisions lead to data which is important, and others are not that important. So that's like the major difference. And in terms of classifying what is important, what is not important, that decision is a split second decision. So usually these kind of small models work in that case. And this is why I have the smallest 165K parameter model. Our target is a 5 class classification in between different types of particles. So the dataset has images, and you have to classify them between whether it's what kind of boson it is, or what kind of quark it is. So that was the task. So I think that should be like well known in terms of what we're getting into. And like I told you, in this case, the two types of instruments, like I gave you an example of a thermometer and a barometer. In this case, those two instruments is an electromagnetic calorimeter and a hadronic calorimeter, right? So these are not just two colors of the same signal. They're two physically separate sub-detectors built for different materials, sitting at a different radii inside the detector. So if it makes sense, if we use a normal attention mechanism like a standard VIT, it throws away the exact reason why we're able to classify the jet. The jet in this case is the detector image. If I like explain it in a very simple manner, so we'll get images of the jets, and then we have to classify what kind of particle it is. Now, the jet is not something which we are well aware of, like in terms of an engine jet. These are images of, I would say, let me just see if I have something on this. I presume I don't, but let me just try and get something in terms of the image. Okay, these are not it. Let me just try. Right. So if I tell you in a very simple way, when two particles collide, they lead to like a particulate, matter which is like spewed out. So that kind of spewing out is a jet, right? And these collide with the detector plate. So the images that we have are for this, and then we need to classify what two particles collided. So this is our task essentially, right? Now if we move forward, and this is the entire architecture. You have two types of channels going into the depth-wise patch embedding, and then the channel-wise attention, which is something novel or new. And then we also have a HAP block. I'll tell you more about it eventually. But what exactly is the best thing about this architecture? The complexity is quadratic on the basis of channel. And if you can see, the number of channels will be very less. There's 2 channels, or if you like scale it up, you may even have a 3-channel based data input. So even in that case, the attention won't increase a lot, right? So this leads to it being very, very complexity, like I would say, efficient. And let me just explain what is the point of HAP. Now, if you think about it, since in this case we have this kind of plate, right? And we're doing this channel wise attention, that means we are going, instead of having attention this way, which is spatially, we want to have attention depth wise, which is pretty fucking interesting if you think about it. So this leads to attention being completely local, right? It leads us to completely get rid of the global relationship that we could have developed. So of course that may lead to still bad results, because they're completely just stripping away all of the global identity and just focusing solely on the local part. So how do we ensure that we have that kind of minimalistic global flavor as well? We can do so by HAP blocks. So HAP blocks basically connect these kind of data inputs along the edges. So we'll have attention between, suppose, this upper layer of patch and this lower layer of patch. So we'll connect them, and then we'll have some attention between the global variance as well. So that includes a good kind of, I would say, interplay between local and global attention, right? Now let's get to the results. So of course I had to figure out, within a transformer architecture, where do I need to put my HAP block, right? So this was the ablation that I had. We can have 12 depth blocks. That is something which is native to our system, a normal, I would say, depth wise attention that we have developed. So that is one case. So the point was how to mix that global attention, right? You can have a DDDH, that means 3 depth blocks and then a single HAP block, and you can do that 4 times. You can do a DDH 6 times, or you can do a DH 12 times, right? So the best result came out for DDDH 4 times. So that's why I took a 25% HAP ratio. Now, another major factor in this entire setup is K, which is a simple knob that allows us to scale the model. I'll get to it as we explain more, but we simply have set a single parameter which you increase, and then the scale of the model shoots up. So it's like a very simple thing to calculate, sorry, not calculate, to like use to scale up the model. So this was the data set, right? the gluon, light quark, WZ, and top quark. These were the 5 classes out of which we need to classify. And this was the multiple particle multiplicity. Okay, so this simply means that in a single image, how many particles are there? 30 particles, 50 particles, 100 particles, 150 particles. So of course 150 particles is the most densest split, which will be used the most for the best kind of results. And these are some of the basic, I would say, metrics. I'll of course add the link to this Medium blog eventually. So what we found out. So first we made up our own model. Okay, it was just a tiny model of 164K parameters. It was 32 times faster faster than the VIT tiny, which was 5.4 million. Okay, so the number of parameters is 32.8 times fewer, and the number of flops are 34.3 times fewer. So we are doing less number of operations per second, and we still reached a 70% top one accuracy, recovering 95.7% of VIT tiny's 73% accuracy. So what was one thing we also got to know, that in this case the scaling of the top one accuracy is pretty tough to, I would say, conjure up. As you'll see, we'll keep scaling up the model and then we'll slowly surpass VIT tiny. So that was the entire point, right? Now we push up the K from 4 to 23. So let me just give you an understanding of how K is working. So essentially, K is the number of summaries that you create for each kind of data representation. Okay, so we have, suppose, an HCal reading. Okay, and we need to have attention along it, like along that depth, right? I do not have a thicker notebook to explain to you that much better, but I guess we can use this. So we can have a depth-wise attention between this. Okay, so how many summaries we are creating of the attention being done over here, that is K. So in a 164K parameter, as a 164,000 parameter, we just have 4 summaries of this kind of attention. If we scale it up to 23, we have a million parameters model. That's the simplest knob to scale up the model, right? Now we close the accuracy gap by to like 0.99 points. And that's the same kind of graph for the same. This is like a split for each kind of class that we have. Now I also tried iJEPA and energy weighted JEPA, and that led to, like, I would say, worse results. The simple reason being that JEPA works best if you have unlabeled data, but in this case and at this scale, JEPA did not help much. So that was like a negative result worth, like, I would say, sharing. Then we scale it up at 5 million parameters and 22 million parameters. So as you can see, we first had a 164K parameter model, then a 1 million one, then a 5.4 million, and then a 22 million. Okay, and slowly we passed the baseline in both the cases, whether we are measuring the macro AOC or the top one accuracy, right? Now the crazy thing about this is, up till 5 million parameters, I just changed the K to like balloon the model to 5.3 million parameters. But when I had to scale it to 22 million, that led to worse things, right? So when the K is 4, the number of parameters that go towards the FFN is 95%. And the channel wise attention is just a measly 1% parameters that go towards it. As we increase the K, the share of parameters that are being used for the channel wise attention, which is something new for us, keeps increasing. Okay? So we're now at K90 and K233. So now 21% of parameters are now being engaged in channel wise attention. But keeping K as 233 does not give the best kind of scaling, because a lot of parameters have now gone towards the HAP. So to scale it much more cleanly, I just increase the number of layers in my model, and the layers at 18. So earlier every configuration had 12 layers, but at scaling the model to 22 million, the share of the parameters that go towards HAP was increasing. So to reduce that share and ensure that the sharing of the parameters is roughly consistent like it was for previous variants of the model, I increased the number of layers to 18. So once we did that, of course we're gonna compare it to VIT small now instead of VIT tiny. VIT small is another publicly available model which is 22 million parameter size. So we did beat that on every class and in terms of the accuracy as well, as you can see the per class AOC. So we did beat it in every class. So that was the one of the major things. Now the last thing which is left up till the progress so far is the complication. So even if we are winning in terms of the flops, right, we are doing less number of calculations once we get the final result out. So the model is quick, but the time that it takes to train the model is much more. Okay, so our DepthViT took 4 times longer to train than a VIT small. So compare it to VIT small took like 5 hours to completely train, while DepthViT took 20 hours, which is like a huge difference. So how do we fix that? We fix that by changing the kernel itself, because a normal CUDA kernel is efficient for 100 by 100 matrix calculations, right? They are efficient for large scale calculations that you only do once or twice. But in our case, we're doing 2 times 2 small matrices. We're doing these calculations across layers. So in a single forward pass, there will be around 300,000 calculations of those small 2 by 2 matrices. So even if the GPU is training well and it is being completely used up, most of the utilization is going towards opening up the memory, getting the answer, and then saving it. So we don't want that. So instead we use Triton, and using Triton we make a custom kernel that only saves the data once and keeps all of the 2 by 2 I would say numbers in its registers. So registers is a very fast memory. So of course we don't need to save it every time because the matrix itself is very small. So that was the entire reason we were able to win on the basis of the wall clock cost as well. So this was the entire accuracy compute trade-off. So as it scales up, we have VIT tiny, VIT small separately as well. And what we actually did, DepthViT was an original architecture which was used for anomaly detection. We repurposed it for classification. So that was the major difference essentially. And now I have to work more towards getting the multi-series evaluations. I do already have that for 22 million based variants, and we are good on that. I do presume to have another dataset in and a channel symmetric VIT control as well. So that was about it. Thank you so much.